Welcome, everybody, and thanks for joining. I'm Kim Oddie, Marketing Communications Manager for Pickering. I will be your moderator for today's webinar. Today's presentation and demo will last approximately 30 to 45 minutes. Directly following, we will have a question and answer period. You can submit a question at any time by entering it in the Q&A section at the bottom of the Zoom screen. Our speakers will answer as many questions as possible following the demonstration, and those not answered will be addressed after the seminar. Please disable any pop-up blockers you may have on your browser so that you can view the presentation properly. Now let's meet our speakers. Tom Sarfi is a business development manager with Pickering. He joined us in 2018 and has over 20 years of experience in product marketing and applications engineering management in the test and measurement industry. He is a past president of the VXI Bus Consortium and is currently our representative on the LXI Consortium Board of Directors. Brendan Casey is the applications engineer with Pickering. He joined us in 2016 and brings test and measurement expertise from his work as an electrical test engineer at Bose Corporation. Matthias von Bossenheim is a SwitchPath Manager software product lead. He started his career with Pickering as a sales and applications engineer in 2004 and brings over 30 years experience in the test and measurement industry. Now I'll hand this over to Tom.
Thank you, Kim. And thanks also to everyone for attending this webinar today. SwitchPath Manager, or SPM as we will refer to it throughout this presentation, it's a software utility that is designed to accelerate the deployment phase of a test system development project. It achieves this by removing much of the complexity that is normally involved in writing the application software that controls a switching system that connects measurement and stimulus instrumentation to a device under test. But before we dive into SPM and how it drives efficiency into a test development project cycle, I thought it would be helpful to describe a challenge we are often faced with in everyday life that relates quite well to Switch software development tasks. Large cities are often a complex network of interconnected and layered streets. Getting from point A to point B can be a challenge, especially if you are in an unfamiliar area. Careful planning may be required to help you choose the most efficient route to get you to the right destination. Not too many years ago, multi-page street atlases were a traveler's best friend, and the amount of planning required to get from a point of origin to a destination was dependent on the complexity of the city to be navigated. And depending on the distance, the travel plan could span multiple and often non-consecutive pages. Fast forward in time, and street atlases are now relics, long having been abandoned for map applications on our mobile devices. Instead of planning each turn, today's traveler simply enters an origin and a destination into the mobile app, and a recommended route is automatically displayed. Virtually no planning is required, and the odds of ending up at the wrong location are actually quite low. Much like navigating from one point to another in a big city, routing an electrical signal between a test instrument and a device under test can require navigating a complex network of interconnected relays, wiring, and interfaces. And for large switching systems, that route a signal takes could be across multiple and often non-consecutive pages of a schematic. Instead of right turns and left turns and street names, the ATE software engineer must determine the correct module identifiers, relay channel names, and switch settings required to establish the desired path between a test instrument and a DUT test point. In this case, routing a test article output signal to an oscilloscope input channel. This can be a time-consuming exercise, and the time required to debug any errors can lead to delays in getting a system fully integrated and into production. Okay, let's walk through a simple example that highlights the challenges that are faced when programming AT switching systems. Even though what I've got displayed here is low on the complexity scale, it'll help us illustrate the points we were making. In this case, there is a device under test that has 32 transmit output ports that are routed through a switching system to either a power meter or a spectrum analyzer input. A switch matrix has been designed to provide the routing between the instruments in the test article. It's designed as a 32 by 1 by 2 matrix and is comprised of 10 multi-throw and 2 Form C microwave relays distributed across 6 PXI modules. There's 45 external coax wires between the PXI modules that are required to complete the routes. Our example involves a test that measures the peak power output of channel 16, or point A, with the power meter or point B. To properly make this measurement, we need to understand the route the signal will travel and then ensure that all switches in the series are set to the correct position. Using a traditional software approach is analogous to pulling out that street atlas book, as we need to study the schematic and note the module IDs or identifiers and switch settings that are needed to complete the path. We start at the output and close the first switch in the series, in this case connecting position 4 on relay K2 of PXI module 2 to its common. You note that the references in the code and to the switch positions COM2 and CH4 pretty generic and meaningless to anyone unfamiliar with the schematic. So going back to our travel planning analogy, it's similar to following the direction to take a left at the second traffic light. Continuing to establish the path, a second call is required, this time addressing module 5. Entering the third layer of relays requires another line of code, this time to control a form C relay. And finally, to complete the path, a fourth line of code is required, this time addressing the second form C relay on module 6. Once this call is completed executing, we can now take our measurement. Doesn't look too bad here, but it's a fairly simple switch system with only one test setup step shown. And it required 4 function calls just to establish one path. But what if there had been a small typo along the way, in this case addressing the wrong relay on module 2? Correct path would not have been established, resulting in test failures and time wasted spent troubleshooting. So we compare once again to trip planning. The question becomes whether we can devise a programming methodology for signal routing systems that provides a user experience that is analogous to using a mobile map application. We would need to provide a programming environment that didn't require the need to study schematics and would allow us to reference signal origin and destination points by intuitive names. We don't want the equivalent of heading the wrong way down a one-way street, so this methodology would also need to prevent connections that could damage the system. We'd want to make this compatible with popular AT application development environments so as not to limit its potential use cases. And if we could do all this, it would seem to offer the potential to significantly reduce the time it takes to get the software code through validation and deployed into production. This is where we introduce Switch Path Manager, an interactive utility that essentially maps a hardware wiring and interconnect schematic into a software configuration file that can then be used to simplify code development. This mapping is a one-time effort in which all external connections between relays and modules, as well as the logical endpoint names, are defined. This configuration file can then be referenced in application code through the SPM application programming interface. And Brendan will show this in more detail in the second part of this webinar. But back to our example. Switch Path Manager utility can be used to define intuitive endpoint names in a configuration file that describes how the relays are connected to one another. Now, just one line of code can be called through the SPM API to correctly set the position of all 4 relays in the path. And note how using the logical endpoint names instead of generic channel name references makes the code much easier to interpret and maintain. SPM also provides a status window that shows the low-level connections that are being made, which can help during troubleshooting efforts. And here's what SPM looks like in a Labview program. It's fundamentally similar to the text-based coding example in that endpoint names are passed to the SPM Labview Connect Endpoints VI. Let's look at another challenge in planning trips, one in which some flexibility in the plans might be required. For example, avoiding highways or other potential conflicts in order to take a scenic route. As you see here, a popular map application, we can avoid highways if we want to take the scenic route, for example, from Mount Rushmore to Yellowstone National Park. And we can build similar flexibility into signal routing software that could also produce significant benefits. A common switch topology in an ATE system is a cross-point matrix, which allows any input to be connected to any output without restrictions. In this example, we have an 8 by 16 matrix, and by closing 2 relays, we can connect input Y3 to output X4, and also input Y5 to output X6. This provides a great deal of flexibility in designing the system, but also presents opportunity for damage to the system if 2 incompatible endpoints, such as 2 outputs or power to ground, are inadvertently connected together. This can be shown in a very simple example where we're connecting a power source and system ground to a device under test through this same cross-point matrix switch. The power source is connected along the Y1 and Y2 axes with the system ground along the Y8 axis. The device under test power inputs and I/O channels are connected across the X-axis. Let's say one test is to verify how the DUT behaves when its power input is shorted to system ground. We can achieve that by closing the relay at the Y8 X1 crosspoint. If the next test requires the power source to be connected to the DUT power inputs, this can be done by closing the relays at the Y1 X1 and Y2 X2 crosspoints. But if we did not include a line of code in between these steps that opens the relay at Y8 X1, we've just created a situation in which the power supply output was shorted to system ground along the X1 axis, likely damaging the relays. SPM is built-in functionality that can prevent this wrong way down one-way street scenario by giving the systems architect the ability to define protection behavior. An endpoint can be defined in the SPM configuration table to be a part of a protection group that restricts allowable connection points. And in this example, we have defined a protection group labeled power and have assigned the DUT 12-volt positive input and the power source positive output to that group. A second protection group labeled G and D or ground includes system ground, the DUT 12-volt negative input, and the power source negative output. Connections can only be allowed between endpoints within the same group. So if a software engineer mistakenly writes code that tries to connect 2 points that are not part of that same protection group or part of a protection group, a runtime error is returned, preventing the connection from taking place and protecting the system from a potentially catastrophic failure. So before we turn things over to Brennan, who will demonstrate the operation of SPM, let's do a quick recap of what benefits it's providing to manufacturing organizations who are developing production test systems. First, by mapping a system schematic into a configuration file, software engineers responsible for developing application code do not need to become familiar with the low-level interconnections between components. They can focus completely on their area of expertise. Defining meaningful names to switch channels rather than generic nomenclature makes code much easier to understand and maintain by production engineers. Path-level programming results in fewer lines of code, which means less opportunity for errors that extend the debugging phase. SPM can also manage potential conflicts in routing, minimizing the chance that undesirable route combinations are created that will cause damage to the system. And all that adds up to a system that will be deployed into production in less time. With that, it's time to turn things over to Brennan Casey, who will dive a bit deeper into the functionality of Switch Path Manager.
All right, thank you, Tom, and thank you everyone for coming. Just wanted to give you guys a quick overview of the Switch Path Manager interface and some of the first steps that you'll go through when you're making your own projects. When you first open this software, you'll see we're going to start with the modules section. This is going to be your starting point for any project. You're going to add any modules that are in your PXI or LXI system. And you can see in our simple example here, we've only got a single module, but it is possible to add multiple modules, and you can also define wiring between them. So when you call endpoint connections, those routings are made automatically. Once you have your modules defined, you're going to move on to the heart of your project, defining the endpoints. You can see in this example, we've already defined a few: the power supply positive and negative, device under test positive and negative, and also an enable line. You can see some of these protection groups that Tom talked about earlier. We have our power, ground, and enable, and they're all set to be protected from one another so that we don't have any shorts that could cause damage to either the test equipment or the device under test. There are also fields to put in your own custom descriptions or user labels to make things more intuitive when you're looking at the system trying to debug things. We also include with the Switch Path Manager a basic softfront panel to use as a debugging tool. And for this example in particular, we have prepared a visual guide so that we can take a look just at our matrix and see what's going on in here. So you can see in our softfront panel, we've got a few of the connections we've defined earlier with the endpoints. And we'll go through and just run a list and see what we have being made with a connection here. You can see we've got the power supply, device under test, and our ground connected. And also enable a connection to our enable lines. And you can see that the Switch Path Manager software will go through automatically selecting the first available Y line to make these connections.
Brendan, people are saying they can't hear you real well. Can you change your...
Oh, sure. Just a moment.
Just before.
How's that? Can everyone hear me now?
That's much better, thanks.
Okay. So as I was saying, we have a list of endpoints already defined here, and the switch path manager software was going to take the first available Y lines to make these endpoint connections. So now that we can see that this is working, we're going to clear out our debugging tool, just move on to what things would look like when you're using a Labview program. So you can see in our basic Labview program, we're using the same sort of structure. We're just using connect endpoint functionality. If you run this, you can see it's doing that same behavior where it's using the first available Y lines to make those connections. We also want to say, for instance, disable one of the Y lines as if we are making it part of a protection group to prevent damage to the device under test. If we run the same program again, you'll see it's automatically skipping that line, moving on to the next available Y line to prevent damage. You can also see an example of the protections available in the switch path manager software. So we know that these two endpoints are part of different protection groups. And let's just see what happens when we try and run those together. You can see the errors are generated, the connections are not made, and your device under test is protected again from any damage. So if we reset this, we can take a look at doing an equivalent operation in Labview without switch path manager. So this would be a fairly similar operation. A similar number of connections are being made here, but the disadvantage is you don't have those endpoint names for intuitive understanding of what's going on in the system. You also don't have those protection groups available. So if we were to, for instance, move this over, you can see now in our display here that we're making connections along the same Y line, which could shorting the power supply positive and negative together. There's no protection here to prevent you from causing damage to your test equipment. So you can see it's a very intuitive system to use endpoints. It's also very safe and protects all of the devices in your testing environment. And with that, I'll just hand things back over to Kim, who will lead us into the Q&A.
Thanks, Brennan. Okay, let's see what we have. Again, you can type any questions you might have down in the Q&A section. We do have a few already up here, so I'll dive right into those. Let's see, the first one is there any license or support contract required? And is there a runtime license for your software?
I can answer this, Kim. The switch path manager requires one license per site. This means it can be used on unlimited number of PCs per site. There is no support contract or support fee, and regular updates are free of charge. So that's why we don't require a runtime license.
Great, thank you very much, Matthias. Okay, the next one is, does SPM work with third-party switch products? Brendan, can you help us on that?
Sure. This switch path manager was created to help our customers implement their switch systems as quickly and as economically as possible. To that end, we only support Pickering products. We have more than 1,000 PXI switch modules available, hundreds of LXI and USB systems as well. So we're pretty confident we have the hardware and software that we need to address any of your test requirements. As Matthias mentioned, any license that you get is a site license, so it covers your entire company. You don't need individual licenses for your PCs where you're doing all of these test developments. So it is a fairly straightforward and economical solution for implementing your test system.
Thank you. Bear with me one sec. Okay, next one is it possible to automatically add modules in the test system? And Brendan?
Yes, I can actually show you exactly where that is. In our first example where we're showing our modules, we have an auto detect feature that will, I'll have to close down the current system, but you can see it has a detect function. In the current system I'm using, there's only one. It's already added, so it's not very exciting to click right now, but it does have the functionality to scan through for PXI and LXI devices available in your test system.
Thank you, Brennan. Got a couple more here. Is Switch Path Manager using the same route all the time? Matthias?
Yeah, I can answer this. Yes, it's always based on the current switch status. The calculated routes are always the same. If there is a sequence, for instance, of multiple routes switched one after the other, the result will always be the same. If something comes in between, then the route will be recalculated and, of course, different.
Okay, thank you. We just had another one come in. How to control the switch card using Python?
I can answer this. There is also an API for Python, so it's using the same functionality, and there's a wrapper for the API functions, which we have in C or .NET. So you can directly use it, like the Labview stuff you have seen.
I can add on to it. We can provide Python wrappers and examples if you would like to try it out. The Python wrappers are supported for both Python 2 and Python 3.
Thank you, Noman. Let's see, I got another one. Can Switch Path Manager handle the routing of different signals through each pole of a two-pole relay? For example, a relay that has two discrete contacts controlled by one control line.
Yeah, I can answer this. No matter how many poles a relay has, 1, 2, or even more, the router always knows in advance whether a relay has to be switched or not. The router verifies if there is a possible and unwanted short on the other pole of that relay before it switches. So there's security built in.
Great. And it looks like that's all the questions we have right now. I think, yeah, that's it for now. I'd like to thank everybody for attending the webinar.